today some of the tasks will be related to the radionuclide tracers applications, but also to one of the very unique technique that is called neutron activation analysis, and we will see how we can apply it for determination of concentration of metals and other components at very low concentrations with very low content. The same parameters or the same dependencies will be also for gamma activation analysis. The principle is a bit different, but so in neutron activation analysis we use neutrons, and in gamma activation we use gamma rays of electromagnetic radiation with very high energy, but all the procedures more or less the same. So first our task is related to this neutron activation analysis. We should determine the mass of arsenicum in a sample that is irradiated to saturation in flux of neutrons with this value, and there are some other parameters are given. So we will start with the basic equation, with the basic idea of the neutron activation analysis. So imagine that we have some object, some target that is irradiated with flux of neutrons. So they are going here, and the flux we will mark as a phi. Due to the nuclear reactions that we already know about the nuclear reactions and neutron-induced nuclear reactions, normally we have an gamma reaction. Not normally, but very often we have this reaction. That means that we irradiate our target with neutrons, and we produce another radionuclide, for example, that emits gamma rays. In this case, initially we have arsenicum 76, so we can write it here. So it's arsenicum 76, and we produce arsenicum 77 that emits gamma rays. So we we have arsenicum 75 in the beginning, and arsenicum 76 as a result. 76, yeah, like this. Due to the irradiation, we accumulate the radionuclide in the sample. So how to calculate the activity of the accumulated radionuclide? For this we have quite a simple expression. So it is the activity of the generated radionuclide will depend, of course, on the flux of neutrons. The larger the flux, the higher the activity that is produced. Then there is a parameter that is called the cross-section of the nuclear reaction. So that is a probability of the nuclear reactions that it will occur. So the higher the probability, again, the higher the activity that is produced. And of course, the number of atoms that we irradiate. If we have a very small amount of atoms, we will produce very low activity. And then there are two next parameters. One of them take into account the density of atoms in the system. So it is minus n. Also the probability and the thickness of the target. And then there is another multiplier that is related to the decay of the radionuclide that is produced. And in this case, it is the same expression as we have in the case of secular equilibrium. Okay. And we'll stop at the moment here. Very often, when we use a very thin target, we can forget about this multiplier, and then the activity will have even simpler form. And now take a look at this expression, and I will remind you how the activity of the daughter radionuclide is accumulated in the case of secular equilibrium. Secular equilibrium. It is the activity, the initial activity of the mother radionuclide multiplied by this multiplier. So in the brackets we have 1 minus exponent in the degree minus lambda, or rate decay constant for our daughter radionuclide, and time of observation. And what is the conditions for secular equilibrium? In secular equilibrium, the half-life of the mother radionuclide is much longer than the half-life of the daughter radionuclide. And now we can compare these two expressions, and we can see that in the case of neutron activation analysis, it is the same equation, and we can assume that when we irradiate our target, that is consists of the stable nuclides, stable elements, we can assume it as a radionuclide with very long half-life. Yeah? And then this activity and this multiplier will be the same meaning. In this case, how will look this accumulation of the activity with time, activity. We accumulate activity, and after one half-life of the our radionuclide that is generated, we will obtain, this bracket will be 0.5 after one half-life. After two half-lives, it will be 0.75, etc. Till the maximum value of activity that we can reach. So this value of activity, so we can write that this value will reach the limit as phi sigma n. Yeah? If time will be sufficient. So in this case, when we say that our target was irradiated to saturation, that means that we reach this maximum activity that can be accumulated in this target. So after a certain time, there is no increase in activity because the number of atoms that are decaying this number is equal to the number of atoms that are generated due to the neutron activation. So it is equilibrium and there is no increase in activity anymore. Okay. There is another point that when we stop irradiation at some point, what will happen next? As far as we produce the radionuclide, it is radioactive. That means that it will decay, and the activity will decrease with time due to the law of radioactive decay. Okay, so now let's move back to our task. We have what we know. We know that the irradiation was to saturation. That means that we will use this simple equation so it is a relationship between the activity and the number of atoms and other parameters. We know the flux of the neutrons. We know, of course, the cross-section because it is a given number. You can look these numbers in databases. And we know activity. Thus, we know everything, and we can find the number of atoms of arsenicum in our sample that were irradiated. So let's do it. So number of atoms will be activity divided by the neutron flux and the cross section of the nuclear reaction. So we have 5 becquerels, or disintegration per second. We have a neutron flux, so it's neutrons per squared centimeter in second. And we have a cross-section value, 4.5 barns. And we remember that 1 barn is equal to 10 to minus 24 squared centimeters, or 10 to minus 28 squared meters. So in this case, it is more convenient to use squared centimeters because we have squared centimeters here, and thus the degree will be this. And we will finally get 5.56 10 to 11 atoms. Okay, but we need to determine the mass of arsenicum. And in this case, mass, it is number of atoms multiplied by the atomic mass and divided by the Avogadro number. So it will be 556. Atomic mass 75, as far as we irradiated our initial arsenicum with mass 75, and divided by the Avogadro number. So finally we will have this number grams. So you see that it is very low mass. It is something like 69 picograms. And that means that with use of such method, we can determine very low masses in our samples. And it is a very powerful technique to perform the chemical analysis when we have very small impurities in the samples, or just imagine that we have very small volume of the sample, like grain of some sample, like soil, or not soil, some materials from the moon. And to analyze, to understand the chemical composition, we can use this neutron activation analysis, because it is non-destructive method. So usually the radionuclides that are generated by neutron activation, they have short half-lives, and that means that after some certain time, all of them will decay to some stable, to other stable nuclides, and that means that after some certain time you will have non-radioactive sample and it is the same sample as you put in the reactor or in the source of neutrons. So yeah, it is a very unique technique and very powerful for chemical analysis. Next task: calculate the minimum time of irradiation that is required to obtain the sample of scandium oxide with a specific activity of this number, 400 megabecquerels per gram. If we have a source of neutrons with a flux of 10 to 11 neutrons per square centimeters per second, and there is information that scandium is a mononuclide element, and there is a cross-section for neutron reactors, and we know the half-life for the scandium that is produced due to the neutron activation. In this case, we will use the almost full equation. What parameters we know? We know the specific activity, and we can calculate it when we divide it by number of atoms that are irradiated. We know the flux, we know the cross-section, we know the half-life, so we can calculate the decay constant, and we should analyze or determine the time. So we know all the parameters that are required to solve this task. So let's take this time from our equation. So first of all, it will be like this. So it is activity divided by all these parameters. Then we should express the number of atoms as a amount of our sample multiplied by the Avogadro number. How we calculate the amount of our sample? It is mass divided by the molar mass and then multiplied by the Avogadro number. But it is important to remember that in this expression, n it is the number of atoms that are irradiated, that are activated by neutrons. In our case, it is number of scandium atoms, specifically scandium atoms. With this expression, we will find the amount of scandium oxide, but not the amount of scandium atoms. If we will look on the formula for our scandium oxide, we will see that it is 2 atoms of scandium per 1 unit of scandium oxide. That means that the amount of number of scandium atoms will be twice higher than the amount of the scandium oxide molecules or units. And that means that we should multiply our expression by 2. And then we will get the number of scandium atoms. So we will put this expression in our equation. So it will be 2, so it will be again phi sigma, then it will be 2 masses multiplied by Avogadro number, and then the molar mass will go to the upper part. And you see that now we have activity divided by mass. And we are asked to find this specific activity. So we can combine this specific activity, so it's activity divided by mass, or per unit of mass, and we will note it, denote it as A with the small letter. So we will finally have this expression: specific activity, molar mass, 2 phi sigma Avogadro number. Okay. And now we will convert this expression to find the time. So we will have finally that our exponent will be equal to 1 minus activity divided by two phi sigma Avogadro number, and that means that T will be equal to minus logarithm 1 minus divided by lambda. And we remember that lambda is equal to logarithm 2 divided by the half-life. So T will be equal to minus our logarithm divided by logarithm of 2 and multiplied by the half-life of scandium. And now we will put all our numbers. So it is minus our specific activity is 400 megabecquerel, so it's 10 to 6 becquerel per gram. Oh, I lost the molar mass, sorry. Multiplied by the molar mass of our scandium oxide, so it is 2 multiplied by 45 plus 3 multiplied by 16. And then divided by 2, the neutron flux is equal to 10 to 11 centimeters second. Then cross section is equal to 27.210 to minus 24 squared centimeters. What else? The Avogadro number, of course. So, and this is our first bracket. We divide it by logarithm of 2 and multiply it. In this case, we can take just days, because we are not asked to find the time in seconds or in minutes or in hours, so we can take what we would like. So, and now try to calculate all these numbers. Finally, the answer will be 2.06 days. So we will need only 2 days for irradiation of our scandium oxide sample to get this specific activity. But we use the equation for the fin target, and that means that we can use this expression for, let's say, small objects like maybe a few milligrams, 100 milligrams, not more than 1-2 gram of the sample. But it will depend on the geometry of our sample, on the geometry of the flux of neutrons, etc. So it is a simplified case, but it is quite illustrative how we can calculate which parameters will affect on the activity of our activated sample, etc. Also, it is a way to produce radionuclides for nuclear medicine, for example, or for research studies, etc. Another task not related to the activation of our target, but it is task related to the radionuclide generator. So we have molybdenum-99 that decays to first technetium-99m, that further decays to technetium-99. And we see that molybdenum-99 has longer half-life than the technetium-99m, and that means that we have a case of the equilibrium, so it's radioactive decay with equilibrium, but the half-lives of the parental radionuclide and the daughter radionuclide, they differ not so much. We cannot say that the half-life of molybdenum much longer than the half-life of technetium-99m, and it is a case of transition equilibrium. And we have to calculate the time after which the technetium-99m, its activity will reach the maximum value. So again, as in the case of secular equilibrium or transition equilibrium, we have an accumulation of the activity of our daughter radionuclide. And then decay of the daughter radionuclide. So we have to find the time that is that related to this maximum activity. So it's activity and time. Yeah, time, activity of our daughter radionuclide. And we remember that in the case of transition equilibrium, the activity of the daughter radionuclide, let's call it just second radionuclide, is equal to to this expression, where index 1 is related to the parental or mother radionuclide, and the index 2 is related to the daughter radionuclide. So this is an expression for activity, accumulation of activity of daughter radionuclide. We see that it depends on the decay of the mother radionuclide, of course, because it produces due to the decay of mother radionuclide. And also, as far as we accumulate the radionuclide, it starts immediately to decay. That's why we have this member in our expression. And to find the time that is related to the maximum activity, we need to find the derivative of our activity, and in this case it is rather simple. So it will be equal. So it is constant value. So we will just put it as C. So all of this is just a constant. And then, as far as it is exponent, it is very convenient to take these derivatives. And to find the maximum, we need to set it equal to 0. So it's clearly seen that constant doesn't affect on the 0 value. Only if the constant is 0, it can affect it. So we need to solve even simpler equation when the expression in our brackets will be equal to 0. And let's rewrite it like this immediately. So we will move all exponents in one side and other parameters in another side, and we will get this. And finally, we take logarithm, and t will be equal So finally we got an expression to find the time where the activity of our daughter radionuclide will be maximum. So now let's put our numbers. It will be logarithm of daughter, half-life of daughter. Yeah, I forgot. Here we have a decay constant, and it will be more convenient to convert them to the half-lives. So again, lambda is equal to logarithm 2 divided by half-life. In this case, logarithm 2 will be annihilated, so we will get the half-life of mother radionuclide divided by the half-life of daughter radionuclide. Then, in the bottom part, we will have logarithm 2, and then it will be difference in half-lives in the bottom part, and the product of these two half-lives. So now we can put our numbers in this expression. So 2.8 days we should convert in hours, because for technetium-99m we have half-life in hours, divided by logarithm 2. Then it is multiplication of, again, two hours. So let's calculate this. So I got this number, 24.5 hours. So after 1 day, the activity of our technetium-99m will reach the maximum value. And again, just to remind you that in this case, so it's activity. The activity, let's take, the activity of molybdenum will decrease with time due to the main law of radioactive decay, and the activity of technetium will grow to some maximum value, and then will go down due to the decay of the mother radionuclide. But at this point, at 24 hours, we can elute it, so the activity will be again 0, and after elution it will accumulate again, and we can elute it again. So, and we can use the molybdenum-99 source for a very long time, and for production of technetium-99m. So this is again how the radionuclide generators are working. Okay, so let's go further. So now let's go a little bit back. It is how we can not estimate. This is just an example how important to understand that the radioactivity, even if it is very high, like several megabecquerels per milliliters, but it doesn't mean that amount of the atoms is very large. Very often when people see high activities, they think that there are a lot of elements, like few grams, I don't know. But in this example, we will see that the amount of radioactive substances, even at high activities, may be very small. It, of course, depends on the activity, on the half-life of the radionuclide. So we have a solution of strontium nitrate with so it is 50 milliliters of the solution with concentration 10 to minus 7 mol per liter, and we add just 1 milliliter of strontium 89, so it is a radioactive tracer with a specific activity of around 50 megabecquerels per milliliter. And we should determine the activity of the solution after the adsorption of the cations of strontium on the glass, so it's just the walls of our glass, and the area of these walls is around 10 squared centimeters, so it is some vial, small vial, and the area occupied by one ion is assumed to be equal to 5 to 10 to minus 19 squared meters. Okay, so first of all, we can estimate the number of atoms that will be adsorbed by the glass. So adsorbed. In this case, it will be equal to the surface of our glass divided by the surface of one ion. So, and we can calculate it quite easily. We have 10 squared centimeters, and we have 10 to minus 19 squared meters, and we have to convert this one to another. So 1 squared centimeter is 10 to minus 4 squared meters. So it will be 10 to minus 3 divided to 10 to minus 19 at 10 to 16, 10 to 15, so 2, 10 to 15 atoms. Okay, it is number of atoms that are adsorbed on the glass. The amount will be equal of adsorbed atoms will be equal to number of atoms divided by the Avogadro number. 3.3 10 to minus 9 moles. Okay. And let's calculate the number of the amount of strontium in our initial solution. So N0, let's say, will be equal to our initial concentration to the volume, initial volume of the solution. So it is 10 to minus 7 mole per liter multiplied by the 0.05 liter. So 50 milliliters, it is 0.05 liters. So it will be equal to 5, 10 to minus 9 moles. Okay, and we see from these numbers that the number of adsorbed atoms is more or less close to the number of atoms in our initial solution. So we will have that the activity, so initial activity, let's calculate it first, is rather simple to calculate. It is 1 milliliter of our solution of strontium 89 multiplied by its specific activity expressed in megabecquerels per milliliter. So it will be just equal to 47.7 megabecquerels. Okay, and the activity after adsorption with time, let's say, will be equal to the number of atoms that are still in the solution. So it is N0 minus N adsorbed divided by the number of atoms in initial solution, and then multiplied just by the initial activity. So, and we know all these numbers, so it will be 5 minus 3.3 divided by 5. So we can neglect all this 10 to minus 9 because they will annihilate, and multiply by 47.7 megabecquerels. So it will be 16.2 megabecquerels. So you can see from this example that if we have a small amount of radionuclide in the solution, in this case we have even stable strontium in the solution, so it's not just a radionuclide tracer, but still the amount is very low, and without any additional sorbents or extraction or precipitation, whatever, the activity of the solution will be changed just due to the adsorption of the strontium atoms by the glass walls. And that is very important to understand it, because it is important to check the absorption capacity of your vessels if you use glass vessels for experiments, etc. Because you can have adsorption of radionuclide just by the walls of your vessel, and you can, after some series of experiments, if you forget about it, you will think that there is a decrease of activity due to, I don't know, some specific processes, due to the extraction or co-precipitation or whatever, but it's just the absorption on the walls. And let's look on the half-life of the strontium 89. Just a moment. So the half-life of strontium is equal to 50 days. .5 days. Let's calculate what is the amount of strontium if there were no stable strontium. What will be amount of strontium 89? Again, it is activity is equal to lambda n. That means that number of atoms will be equal to activity. So we know the activity, that's 47.7 10 to 6 megabecquerels divided by logarithm 2 multiplied by the half-life in seconds. So it is days, hours, seconds. So it will be just 3 10 to 14. And if we compare this, so atoms, yes, atoms. That means that all these atoms, all the activity of our strontium 89 would be sorbed on the glass if there were no stable strontium. If we didn't add some stable trace, not trace carrier. So again, it is important to remember that very often, so this activity, 50 megabecquerels, let's say, per milliliter, is very high activity, but still there are only few atoms of the radionuclide. So don't forget about these relationships. So let's go further. So the next is the related task. In this case, we would like to obtain some particles or gel or whatever with some specific surface activity. In this case, we sorbed zirconium 95 on silica gel with the known surface area. We know that the sorption efficiency is only 40%, let's say, and we know the area that is related to one zirconium atom. So again, it's a rather simple task, but we will go through it. First, what we would like to know, it is the number of atoms per gram of the silica gel that can be, so number of atoms that can be sorbed per one atom, per 1 gram of silica gel. So we know the surface, specific surface of our gel, and thus we can calculate the number of atoms if we divide with this surface by a number of by the area of one ion, but we have to multiply it by 0.4 because only 40% of all the places will be occupied by the zirconium atoms. So let's do it. It will be 80 squared meters, 0.4, and here it will be 5 10 to minus 15 squared centimeters. So again, we should not forget to convert centimeters to squared meters, or vice versa. So it will be 6.4 10 to 19 atoms. Okay, so we know the number of atoms that can be sorbed by the silica gel, and now we have to find the specific activity that will be equal to our, so it's atoms per gram of the sorbent. Fortunately, we already have a lambda value in our task. So it is 125 10 to minus 7 second multiplied by the number of atoms. So it will be 8 10 to 12 becquerels per gram. Okay. So it is quite high specific activity of our silica gel, and why we can use it, because one of the way to deliver radiopharmaceuticals to the organ is the use of this labeled nanoparticles. So if we know the specific activity of nanoparticles, and if we know what is the efficiency of sorption of our radionuclide on these particles, we can easily calculate the activity, specific activity of the nanoparticles, and then with this knowledge we can calculate what will be the dose that will be formed due to this activity, due to the energy of the irradiation, etc., etc. Okay, let's go through them. And this task will be the last for today, and we'll see what is the dose, adsorbed dose inside our body is formed due to, or generated due to the decay of the natural radionuclide of potassium 40. It is known that the content of potassium inside the body is around 0.25 weight percent, and we know the content of this natural radionuclide in natural potassium, and we know the half-life of the potassium 40. You see that it is quite a large number. That means that potassium 40 is primordial radionuclide. It was on the Earth since the beginning of its formation, and will be longer after us, and there are also data about the decay modes, decay types of the potassium-40. The main probability, the main yield, the main type of the decay is beta minus decay with the probability of 89% and with the maximum energy of beta particles equal to 1312 kiloelectron volts. There is electron capture that is accompanied by the emission of gamma quanta with energy of 1460 kiloelectron volts. So to estimate the dose inside our body, we have to calculate the energy that is transformed or generated due to both beta decay and gamma decay. So in principle, the dose should be the sum of doses generated by beta and gamma radiation. But we have to understand that dose, it is absorbed energy, and the gamma radiation has very high penetration ability. That means that absorption of gamma quanta inside the body will be very low. Also, the probability, the amount of gamma quanta is relatively low. It's only 11% of all the decays. So only 11% will produce this gamma rays, and only part of this 11% will be absorbed by the human body. If we calculate more precisely, we will see that it will be equal to 3 to 4%, maybe even less, of the whole contribution of gamma quanta to the internal dose of human body. So that means that we can neglect it, so the dose is almost equal to 0, and calculate on the dose that is formed due to the beta decay of potassium-40. How to calculate this dose? So, dose from beta, it will be the energy of the beta decay, of course, but we remember that the spectrum of beta particles, something like this, with maximum energy. And to calculate the average dose, we have to take the average value of the energy of beta particles, and it will be equal to 0.4 multiplied by the maximum energy. So we need to take this average energy of beta particles. We need to know how many particles are emitted during the whole year. So it is the activity multiplied by the yield of the beta particles, so it is 89%, and the time, so 1 year. So it will be the number of beta particles that are emitted from due to the decay of potassium-40, and divided this all by the mass of the human body. So now let's write more specifically the activity. Activity is equal to lambda n. Okay. Lambda is clear. What about n? N is the amount of the potassium multiplied by the Avogadro number. So all this clear. What is the amount of potassium 40? So let's write it here. So Avogadro number. The amount of the potassium 40, it is mass of potassium 40 specifically divided by this atomic mass. Okay, and now what is the mass of potassium 40? Mass of potassium 40, it is mass of potassium multiplied by the fraction of potassium 40. And the mass of potassium, if we know its content in the human body, it is the mass of the human body, just body, multiplied by the content of the potassium, the whole content of the potassium, and again the fraction of potassium 40 in potassium. So we should put all these values here, and finally we will have this expression for those. So again, it is energy of beta particles, activity, now it's logarithm 2, Avogadro number, mass of potassium 40, so it's mass of our body, fraction of potassium 40 in potassium, then yield of the probability of beta decay, time, and now it is mass, half-life, and atomic mass of our potassium 40. So we can remove the masses, and that means that we know everything. And let's put it here. So 0.4 energy. It is this energy 10 to 3 electron volts, but we need to calculate the dose. Dose, it is joule per kilo. That means that we have to convert electron volts to joules. So it's joules electron volt. Then what next? Activity. Not activity, sorry, logarithm 2, Avogadro number, fraction of potassium, so it's not 0.025, 0.4 minus 3 minus 19, logarithm 2, Avogadro, fraction of potassium, fraction of potassium 40, probability, and let's take a time just 1 year, because the half-life we also have in years, so it will we don't need to convert years to seconds or whatever. So here it will be half-life, and the atomic mass we should take it 40, but not grams, but kilograms, because again absorbed dose, it is joule per kilo. So the final number will be 177 10 to minus 4 gray, if it is absorbed dose. And to calculate the equivalent dose, we have to multiply this absorbed dose to the Wien factor for beta radiation. Fortunately, the Wien factor for beta radiation is equal to 1, and thus we can say that it will be equal to the equivalent dose. And we can say that this equivalent dose in our case will be 0.177 millisievert, and this is dose per year. Yeah? So around 0.2 millisieverts per year we receive from the potassium 40 that is located inside our body. And we remember that the average annual dose is around 2 millisieverts, so around 10% of the whole dose we receive from our body, from our potassium that is inside us.